Hello, everyone. This is Group 1 for the Stat 512 final group project. We are looking at the impact on nutritional information on calorie totals. My name is Dylan Cologne.
My name's Ev Borwinkle.
I'm Satya Bonipali.
Jorge Mendoza.
And I'm Shen
Absolutely. And real quick, we're just going to give some background information of our project. We're going to discuss some of the results that we had, the questions that we researched, and a quick introduction into the data of our project, just so you get a little bit more familiar when we start talking about our individual questions individually in specific, going into all of the actual work that we did for the project and our conclusions of them.
So for the background, we wanted to understand the factors that influence calorie content in food. It is essential for improving dietary recommendations, nutrition labeling, and consumer health. So this is related to our everyday life. And based on that, we found our data set and listed the list of questions is listed on the right side.
All right, and then our results of each of those questions. So the first question, we found that vitamin B12 and meat have the strongest interaction of all the interactions between iron and food categories and vitamin B12 and food categories. And our second question, we found that fat and cholesterol do not have an equal impact on the amount of calories in 100 grams of food. And our third question, we realized that processed foods, net carbs, fat, and protein has significantly influenced calorie content, sugar, and cholesterol, but do not statistically impact in this model. In the fourth question, we realized that protein net carbs have a significant positive impact on calories, while iron has a significant negative impact on calories. And in the last question, we found that iron, zinc, and vitamin B12 do not have a significant impact on calories, given the protein, carbs, and fats are in the model. So now we're going to go into our data.
As for the data, we have that our y variable is calories. So that's how many kilocalories there's per 100 grams of whatever the food item there is. The x1 variable is the category name. So it's the food category, which is our categorical variable. And then x2 is sugar, which is the amount of sugar per 100 grams of a particular food item. X3 is cholesterol, which is how many grams of cholesterol we have per 100 grams of a particular food item. X4 is carbs, which is the same thing for the amount of carbs. And then X5 is fats, X6 is protein, X7 is iron, X8 is vitamin B12, and X9 is zinc. So that's how many grams of zinc we have per 100 grams of a particular food item.
To begin, research question 1 asks us to look at how iron and vitamin B12 interact with different categories of food, which is limited to fruits, vegetables, meats, and dairy. We then want to know which of these interactions has the greatest impact on the total amount of calories in 100 grams of food. To address this research question, we begin with our hypothesis. If the results from the analysis are insignificant, we will conclude the null hypothesis that the interactions have no impact on calories. If our results are significant, we can reject the null hypothesis and conclude the alternative hypothesis that at least one of the interactions have a significant impact on calories. From there, we can read the coefficients to determine which has the greatest influence. These hypotheses will be tested using this model, which includes vitamin B12, iron, the categories, and interactions between iron and category in the vitamin B12 category. Before making any interpretations on the data, we must first look at the data and diagnose any violations against MLR assumptions. To do this, a correlation matrix heat map was used to detect any high collinearity between variables as seen above. A box plot was used to show the spread of data in each category. Scatterplots and VIF were used to diagnose any multicollinearity issues. None of these diagnostics presented big issues. However, a number of outliers were identified using PF betas, hat values, and Cook's distance. There were also issues with non-normal residuals, which was detected using the Shapiro-Wilk test, which had a significant p-value. There was also an issue with non-constant variance, which was identified using the Broich-Pagan test and a significant p-value. To address these issues of non-normal residuals and non-constant variance, all identified outliers were removed. Additionally, Box-Cox transformation was employed using the optimal lambda, which is identified in the graph where lambda was 0.141. You can see from the residual plot and QQ plot this is greatly improved in the model. Weighted least squares, standard variables, and additional Cook's distance were also used but ultimately dropped either due to relevance or insufficient changes to the data. These improvements were still not significant, however, as the Shapiro p-value for this model is still 0.0341, and the Broich-Pagan p-value is 0.005699. These values indicate that non-constant variance and non-normal residuals are still problematic, however they're better than before. This should be considered when the results are interpreted. To validate the model, bootstrapping and a tenfold cross-validation were conducted. Bootstrapping, performed with 1,000 resamples, provided estimates on bias on standard error of the coefficients. The intercept had a bias of negative 0.379 and a standard error of 0.919, with a 95% bias corrected and accelerated confidence interval of 5.343 to 8.992, indicating that their intercept is robust. Cross-validation was used to evaluate model performance. The tenfold cross-validation yielded an RMSE of 1.014 and an R-squared of 0.721, indicating that the model performs reasonably well in predicting new observations. The points of the predicted versus observed plot generally align with the diagonal reference line, indicating good agreement between predictions and observed values. The f-test comparing the interactions of vitamin B12 and iron across food categories resulted in a highly significant p-value, less than 2.64 times 10 to the negative fifth, indicating that the differences between these interactions are statistically significant. From the coefficients in the R output on the right, it can be observed that the interactions of vitamin B12 with meat has the largest negative estimate of negative 8.13 times 10 to the fifth on the confidence interval from negative 1.523 to negative 1.042.
As for research question 2, we wanted to see if the contents of fat and cholesterol has an equal impact on the amount of calories in 100 grams of whatever the food item is, given that sugar, net carbs, and protein are present in that food item. The null hypothesis, we equated the two and put the coefficients for the other variables as the given constants, and then we also had the alternative hypothesis defined with the reduced and full models and the respective degrees of freedom. When model diagnostics were performed, we noticed that there was a normality violation because the Shapiro-Wilk test outputted a p-value of 2.2 times 10 to the negative 6, which is significantly lower than the assumed alpha value. And then with the non-constant variance as well, there was an issue there because the p-value that was outputted in the Broach-Pagan test was also lesser than the assumed alpha value. X2 from the added variable plots was noted that it didn't contribute much in the presence of the other predictors. So that variable was dropped and outliers and influential points were also detected. This was done through the hat value for X outliers and studentized deleted residuals for Y outliers. Influential points were detected through the Cook's distance method. Finally, with the hypothesis testing, the results was that the F statistic outputted was significantly higher than the critical value, and the p-value was also noted to be lesser than the alpha value. So the null hypothesis was rejected. This means in our case that the interpretation with a correlation of the data set explored and the hypothesis tested means that the fats and cholesterol do not have an equal impact on the amount of calories in 100 grams of food, which is consistent with the literature review performed at the beginning of testing the research question, since the body requires different amounts of fats and cholesterol, which would mean that the impact is different.
Hello, everyone. Research question number 3. How do sugar, fat, and net carb correlate with calories in processed versus unprocessed food? My project explores how calorie content is influenced by sugar, fat, and net carbs with a focus on differences between processed and unprocessed foods. Usually processed foods are often linked to a higher calorie count, but I wanted to test whether it's true or not. Here's my initial hypothesis, my new hypothesis, and alternative hypothesis. In the figure down to the right, group 1 is usually unprocessed or minimally processed foods. This is considered unprocessed in this project, and the rest of group 2, 3, and 4 are considered as processed food. So a new categorical variable of processed is introduced, and if a food lies in group 1, I give it a value of 0. If it lies in the other group, I give it a value of 1. So to test my hypothesis, I fit a linear regression model, including sugar, fat, net carbs, and their interaction with the process variable. Here's what I found initially. There's a normality violation. Shapiro-Wilk test has a p-value of 0.0022, and also BP test has a p-value less than 2.2 times 10 to the negative 6. But the adjusted R-squared originally is 97.5%, indicating strong explanatory power. However, the QQ plot of residuals showed the divisions from normality as I identified an outlier using Cook's distance. So how to improve the model to address these issues? I removed the outlier and refit the model. After the removal, the residual showed a better alignment with normality in the QQ plot. Also, the model residual standard error decreased, confirming that prediction was more precise. I also performed a WLS test to handle the heteroscedasticity. This adjustment provided more reliable coefficient estimates and further validated my model. Now here's my testing final results. The interaction term between processed food and net carbs was significant. Also, fat and net carbs have been consistently strong, predictors with a significant positive coefficient. However, sugar's impact was not significant, suggesting there might be further research needs to be done to this project. Also, in summary, this project used stats in uncovering differences between processed and unprocessed food and removing the outlier, applying the WLS greatly improved my model reliability, confirming that net carbs and fat play a major role in calorie counts in the processed food. And surprisingly, sugar's impact was not significant. Thank you very much.
Hello, this is Dylan Colon, and I'm going to talk about research question 4, specifically about if protein will have a significant impact on the amount of calories and 100 grams of food given net carbs and iron is considered. Some background information on all of this: calories and macronutrients. Calories is the energy derived from food that is dependent on the composition of carbs, protein, and fats. Protein specifically, its effect is that it has a high thermic effect, meaning it has required more energy for digestion compared to carbs and fats. So I'm looking to investigate protein's unique impact on calorie count, considering carbs and iron levels. Some important information about this, we can gain some insight into dietary planning and nutritional optimization. So in my hypothesis analysis, you can see my null and alternative hypothesis in my models. The difference between the full and reduced model is the absence of protein in the reduced model. So the actual diagnosis of these two reduced and full models is seen here. And as you clearly see from the R squared and other values, is that our full model is going to be a lot more representative of our data. So that's the model I decided to go with. That being said, there were a lot of issues with this model on first diagnostic checks on my initial go through. The normality of residuals, heteroscedasticity, multicollinearity, and the outliers were all over the charts. There were a lot of values that I needed to deal with, and so some things needed to be improved. Speaking of improvements, to address the normality of residuals, I did log transformation of 1 plus y due to the fact that some of the calorie count was 0, so I had to increase them by 1. And for heteroscedasticity, I used a weighted least squares transformation. For multicollinearity, a bootstrapping method was attempted. However, as you'll see in the next slide, wasn't as effective as other methods. The outliers and higher leverage identified and removing as many influential points as I could. My final diagnostic looks a lot better with my normality of residual plots looking good. My multicollinearity BP tests had a value of 1, which is passing, and my heteroscedasticity, we're looking for a value of 10. However, those values aren't, so that has to be considered in our final analysis. Also, looking at our outliers, we could see that the Cook's distance test and HAT matrix have a lot better than before. So what does this actually mean? We found that a positive coefficient for each unit increase in protein and as well as carbs. However, iron has a negative impact. What does that kind of mean in layman's terms? So in summary, long story short, we could see that protein has significant impacts of calories when combined with carbs, whereas protein and iron has a negative impact. That being said, you could think of high iron, high protein foods of having a lower calorie count, like tofu. If you're looking for something for a more higher calorie count, if that's something you're looking for, you could think of high carb foods with high protein, like chicken, meat. Also, these like protein tortilla chips that I found as well. Those are great alternatives as well.
Our final research question turns its focus towards the meat category. We want to address whether iron, zinc, and vitamin B content has a significant impact on calories, given that protein, fats, and net carbs are present in the model. Previous research has identified that proteins, fats, and carbs are the primary sources of calories in a diet, and that these have 4, 4, and 9 calories per gram respectively. It has also been identified that meats are especially rich at zinc, vitamin B12, and iron, which are essential for energy extraction processes. We suspect that iron, vitamin B12, and zinc do not have a significant impact on calories. and our alternative hypothesis is that at least one of them is significant. Our initial model presented two main issues: influential cases and non-normality of residuals. We did not observe a curvilinear pattern or residual plots and added variable plots, which is why we stuck with the linear model. We also identified that there is constant residual variance and no multicollinearity. To improve our model, we used a Box-Cox transformation to address the non-normality, and we used a lambda of 0.99 as suggested by the log likelihood. Our robust regression used a Hubbard weight function, which was selected through a tenfold cross-validation to address influential cases. Observation 464 remained an influential case even after robust was used, which is why we decided to remove it. Our final model still had a non-normality issue, and it had our RSME of 3.72 and an R squared of 0.99, according to our tenfold cross-validation. A general linear test was used to test our hypotheses, and we failed to reject the null hypothesis. Hence, vitamin B12, iron, and zinc do not have a significant impact on calories. Our estimated linear impact of proteins, fats, and carbs were in accordance to previous research. Finally, it is suggested that future predictions with our model are kept to mean responses due to the non-normality assumption violation.
Some advice
All right.
some
No,
advice for future statisticians to take time to ensure that you truly understand your data, to understand how your variables interact with each other and the response variable before forming your research questions. In the case of research question one, I was particularly not familiar with how nutrients in food work to interact with each other, and it made it really difficult to analyze data and wasted a lot of time. This was especially evident when results showed that vitamin B12 and fruits and veggies had no interaction, as I did not realize this was due to the fact that they simply do not have vitamin B12 in them.